Okay, good morning.
Good morning, sir.
Yes, just wait. We'll start, okay, for another 2 minutes. Okay, so today we'll take up the problems on beams for calculating shear force and bending moment. Till now, we have worked with the problems on simply supported beams. Okay, so we'll go ahead with the cantilever type of beam. Okay, so let us consider example of cantilever beam. We still have some loadings to be taken up on a simply supported beam, but we'll go with both simultaneously. So in case of cantilever beam, let us say we have a beam over here. Okay, and we have loads which are applied on this beam. So this would be 20 kilonewtons. Okay, and 10 kilonewton, 50 kilonewton. Okay, so this is a 2 meter distance, and here 1 meter and 1 meter. So this is the fixed end of the cantilever beam. So A, let us say this as point B. Okay, if you are not given these points, you can mark these points. There is no problem if you mark these points when you are solving the problems. Okay, sometimes it happens that they just simply mention the beam over there, so you can take these points, right? So this is our beam. For this, we need to calculate the shear force and bending moment. Okay, So at 1 meter interval, okay, and we and plot shear force diagram, that is SFD and BMD. Okay, so this is what you need to do for this beam, what is shown over here. Okay, so first thing what I require is the reactions of the beam at the supports. Okay, so what are the reactions at the supports that have to be calculated? Now, if you take this support A, so this is a fixed support, and for a fixed support, what we have is it can offer three reactions. Okay, so we come across the reactions over here as a horizontal reaction. It can offer a horizontal reaction. Okay, let us say this is HA, and it can even offer a vertical reaction, and let me take it as a VA. Okay, so this is a VA, and in addition it also can have a reaction in the form of a moment. Okay, so this is VA, vertical reaction at A, and reaction in the form of movement at A, MA. Okay, so a fixed support can develop all these three reactions. Okay, that is a property of a fixed support. So what are the values of these reactions in our case? So we'll calculate those values. So here first is support reactions, that has to be calculated. So how do you calculate the support reaction is from considering the condition of equilibrium. Okay, so what we have, condition of equilibrium, this is the first condition what I can apply, summation fx is equal to 0. Summation of forces in x direction should be 0. Okay, so if I look into this beam, what are the forces acting in x direction? So out of these applied loads, none of them are in x direction. They are not directed in x direction. Only this horizontal reaction is coming in picture. Okay, so what it says is this HA is equal to 0. Directly HA equal to 0 because I don't have any other forces which are applied in our x direction. Okay, if these are my x and y direction, so there are no forces which are acting in x direction. So it tells that horizontal reaction at A is 0. That's one result what we got from the condition of equilibrium. Next, if we proceed further by taking second condition of equilibrium, which is summation Fy equal to 0. Okay, so I'll add up all the forces which are acting in y direction. Okay, let us see what we'll get from that. So when I start from A, we have VA. Okay, so this is VA which is acting in upward direction plus VA, and 20 kilonewton concentrated load which is in downward direction minus 20. There is a concentrated load of 10 kilonewton here at C, minus 10 because it is in downward direction, and finally there is one more concentrated load of 50 kilonewton acting in downward direction applied at point D. Okay, so minus 50. When I add all these forces, it should result in 0. It should give me 0, or this will tell us what is our reaction at A, vertical reaction at A. So 50, 10, 60 and 20, it comes out as 80 kilonewton. So the reaction at A is vertical upwards, and it is of 80 kilonewton in magnitude. Okay, so this is what we got here. Now one more condition of equilibrium, if we go for using that one, what we have, summation of moments about A should be 0. Let me take the third condition of equilibrium. Summation of moment should come out to 0, and if I take moment about A, that is at this support A, Okay, what it gives me is there is one moment in the form of reaction which is coming in at point A itself. Okay, so what I have taken for this, I have taken this is in anti-clockwise direction. I assume that MA is acting in anti-clockwise direction. Okay, even if you take in clockwise direction, later you will come to know if it comes out to be negative, then it is in opposite direction. So minus MA, as per my this one, it may be in anti-clockwise direction. Okay, so I have taken in anti-clockwise direction. So minus MA is one moment with at A, and due to this 2, HA is 0, so no question of moment. VA is directly applied at A, it is a reaction at A, so it will be acting at point A itself. So here VA will not develop any moment because there is no distance which is coming in picture between VA and a point A. Okay, so moment due to VA is 0 or VA into 0 it will come out. And next is this 20 kilonewton load. Due to 20 kilonewton load, what I have about point A, there will be a clockwise movement. Okay, this 20 kilonewton load will have a clockwise movement about point A. So, and what will be the magnitude? So I'll take it as plus, clockwise I'm considering positive. So here 20 into distance is 1 meters, 20 into 1 meter. Okay, then this 10 kilonewton load, it will have a clockwise movement about point A. So 10 into 2 meter, 1 plus 1, 2 meters. So since it is clockwise, plus here 10 into 2 meters. Okay, then this 50 kilonewton load, what it will have? It will also have a clockwise movement about point A. Okay, it will try to rotate this beam in a clockwise direction about point A. So plus, right? And what is the magnitude? Load or force multiplied by a perpendicular distance. 2 plus 1, 3 plus 1, 4 meter. 50 into 4 meters here. So this should result in 0. Okay, when you add up all the moments in the beam, it should give you 0. Or what will happen? It will give us the value of MA here. So it will be 20 plus this is also 20, 40 plus this is 200. That will come out to be 240 kilonewton meter here. Okay, so we got all the reactions at support A. Okay, that is VA and MAR here. Now we can go for plotting the or calculating the shear force and bending moment. Okay, so first is we'll go for calculating shear force here. Okay, so we used to take the section. Okay, we used to take a section and move the section by the given interval, right? So normally we went for taking the section from left end and we started moving towards the right end of the beam. Okay, now in case of cantilevers, okay, it will be convenient or it will be a little bit easy if you place your section towards right. Okay, if I start from right end of the beam. Okay, so that is the advantage for us. It will be simpler for us to calculate the shear force and bending moment. If I place it here, so it may become slightly difficult when we go for calculating the bending moment. Shear force will not be any difficulty whether you take it from left or you come from right, doesn't matter. But when it is a question of calculating the bending moment, so at that time there may be slight difficulty or confusion. So in this case, in case of cantilever beams, okay, so we'll go for taking the section from the right end of the beam. Okay, we'll consider a section at this end, okay, starting from D, and we'll move it towards the left end. We'll move it towards end A or towards the support A over here. So let us say this is our starting point. So when I am at D, okay, initially shear force just to right of D, okay. So just to the right side of D, what I don't have any other loads which are being applied over here on the right side of D. So no forces are there. So what it results is shear force is 0 over there. Okay. So at that point it is 0. Now when I cross this 50 kilonewton load, which is directly applied at D, okay. So what happens there? left of D. What happens? Once I cross this 50 kilonewton load, once my section is placed to the right side of D, now I can consider this 50 kilonewton in my shear force calculation. Okay, so the magnitude will be 50. What about the sign? Okay, as per our sign conventions, okay, when the section, when the force was to the left side of the section, if it was upward, we used to take it as positive. This was our positive sign convention. Okay, on the other hand, if the force is to the right side of the section and if it is upwards, then we should have taken it negative. Okay, this is our sign convention for the shear force. Okay, one is when we are taking the forces from the left side of our section, if the forces are coming out to be upwards, then it will be positive. Okay, now what we are doing is we are looking to the right side of our section, in the right side of the section. Okay, so on the right side of section, this 50 kilonewton load is acting in downward direction, so it is positive. Right side downward force is positive. Okay, so it will be plus 50 here. Is that clear how I took the sign for the shear force? Earlier this was applicable because the section what we had, okay, we used to take sum of all the forces to the left of the section. So I was referring to this. If this is if the forces they were resulting in upward direction, then positive, else negative. Now my section, what I'm doing is I'm considering all the forces to the right of the section over here. My section is here to the right side of D. So I'm taking sum of all the forces to the right of my section. Whatever forces are there on the right side of my section, I'm adding them. Okay. So here I have only one force, this 50 kilonewton force. Okay, this one. Okay. So and what is the direction of this force? It is acting in downward direction. Okay. So if I compare this with my sign convention, right side downward force, what is there? It is positive. I should take a positive sign for that. Okay. So for that purpose, I'm keeping it as plus 50. Okay. So that is the sign convention what we'll adopt over there. Now, after this, what we have to do? We have to move to the next interval. Okay. So my next interval is at a distance of 2 meters. Okay. At every 1 meter interval, you have to calculate the shear force. So shear force at a distance of what 1 meter. Okay, I did it just to the left and right side of the section. Okay, now my first interval will be at a distance of 1 meter from D. Okay, from point D. These two values are at point D itself, 0 and 50. Okay, there is sudden increase in the shear force over here. Now when I move to a distance of 1 meter, what happens at that point? Again, there is no other force other than this 50 kilonewton load. Okay, so what I have is only this 50 kilonewton load. Okay, so what will be the value of shear force? It will be just 50 kilonewton over there. So this will be again 50. What about the sign? It will be plus. Why? So the force is to the right side of my section. Just 1 minute. Okay. So the force is to the right side of the section, and what I have is it is in downward direction. Force is to the right side of my section and acting in downward direction. So this particular sign convention indicates that it is positive. Okay, so plus 50. Now after 2 meter interval, what will happen to the shear force? Okay, after 2 meter interval, there is a concentrated load over here. Okay, so I'll have to check what will happen to the shear force before I cross this load and after I cross this load. Okay, before crossing this load, what will be the value of shear force over here? Okay, just to the right of C, and once I cross this concentrated load, what will happen to the shear force value? Okay, that should be known to us. So here shear force at a distance of 2 meters, you can calculate with your paper and pen also. Shear force at a distance of 2 meters from D. Okay, I want to calculate shear force at a distance of 2 meters from D. Okay, but what is there? There is a concentrated load. So what I'll consider is shear force just to right of point C. Okay, so it will again come out to be 50 kilonewton. Okay, when I'm to the right side of this point C over here, what I have is only 50 kilonewton acting in downward direction. So sign convention is for positive, so it will be plus 50. Now if I cross this point, okay, say now once I come to the left side of this point C, now there what it will be giving me the shear force just to left of C, left of point C. What will happen? So 50 acting in downward direction and this 10, 60, totally 60 kilonewton, and it is acting in downward direction. So what will be the sign I should assign? Right side. Okay, section is somewhere here. Okay, let me bring this section over here now. So right side of C, and the net force is in downward direction. Okay, so because of that I should adopt a positive sign for that. So this is my section right side of C. Okay, and what is the total force? This 10 plus 50, 60 kilonewton. Magnitude is 60 kilonewton, and both are in downward direction. That's why I can directly add them. 10 plus 50, 60. Resulting force will also be in downward direction. So right side, my section is here. You may say this is my section XX. To the right side of this section, the total force is 60 kilonewton and acting in downward direction. So this is applicable. Okay, right side downward direction. So the force or shear force value will come out to be plus 60 over here, plus 60 kilonewtons, right? So we got the value of shear force after a distance of 2 meter from D. Okay. Next, again, I'll have to move by 1 more meter. Okay, that is the interval given to me. So I'll move my section by another 1 meter, where I'll be, if I move by 1 meter, I'll reach point B. Okay, so at point B, I'm having a concentrated force. So whenever I come across concentrated force, I'll go for checking to the left of that force and to the right of that force. Okay, so here what I should do is we are going to calculate the shear force value. Shear force at what distance? At a distance of of 3 meters. I'm increasing 1 meter by 1 meter interval. Okay, from D. Okay, so since there is a concentrated force which is of 20 kilonewton here, okay, 20 kilonewton is applied at a distance of 3 meter from D. I'll go for first taking my shear force calculation just to right of B. Okay, what I'm doing here is my section first I'm placing just to the right side of this B. I'm not crossing this 20 kilonewton load first. Okay, so I'll take the shear force, calculate the shear force. What is happening here? 50 plus 10. Okay, downwards. 50 is also downwards. 10 kilonewton is also downwards. So 60 kilonewton downwards. So this itself plus 60. So it is still plus 60. Okay, and once I cross this concentrated force, okay, now what I'll do, I'll move my section to the right, left of this point B. Okay, I'll place it over here on this side to the left of B. Now you go for calculating the shear force here. What happens to the shear force? Left of B. So what are the forces to the right side of this section? 50 downwards, okay, 10 it is also downwards, so 50 plus 10, and this 20 kilonewton force is also downwards, so 50 plus 10 plus 20, that will be 80 kilonewton, okay, and resulting force will also be in downward direction. So any force to the right of section acting in downward direction will be positive, it will be assigned a positive sign. So here it is 80 kilonewtons, okay, and this will be continuing up to point A. Okay, to the right side of point A, it will be still 80. Once I cross point A, what will happen? This 80 plus VA, which is again 80 upwards. So both will become zero. They will result in zero. So that is the shear force value at that point A. Okay, so at A, again what you have to do is take the section just to the left of A and right of A. Why I'm telling again and again to the left of A, right of A, or to the left and right of any concentrated load is, you should not, while plotting, it should not happen thus. Your point is here, okay, and you plot something like this. It is not varying linearly between these over this range, okay. There is sudden change in the shear force when you cross the point. So that's why we go for calculating that shear force value just to the left and right side of the concentrated load. Now what happens here? Shear force at a distance of okay 4 meters, okay, 4 meters from from point D, okay. What will happen here? So I'll go for calculating shear force to the right side of point A, okay. So it will be equal to what? 50 plus 10, 60 plus 20, okay, 80 kilonewton and downwards, okay. That will be the only force which are acting over here. So this is how my section is at present, and take the sum of all the forces to the right side of this section. It is coming out to be 80, and that 80 kilonewton force is acting in downward direction, right side downward direction force. So it will be positive. It will be considered to be positive, 80 kilonewtons, positive. Okay. So once I move my section just to the uh, left of A, okay, to the left side of A, what will happen now? Over there, that reaction at A will come in picture, okay. So when I come to the left side of A, okay, slightly to the left of A, so, and when we calculate the shear force here, it will be 50 plus 10 plus 20 minus 80, because this is in opposite direction to these forces. So it will come out to be 0, okay. This is the shear force variation in this beam. At least in the beginning, we will be following this in detail shear force calculation, okay. Later we can do it quickly, but till you are familiar with this calculation. Is there any doubt in that part? Actually, you can put these values, okay. I have directly equated the sum here, but you can add up one by one over here and you can put those. If you have any difficulty in this part, please you can come and ask. You have to refer this video only for the notes, because the moment I exit this meeting, this screen what I have written will be gone. You can better write it down in your books while watching itself. Okay, I'll erase this part and we'll go for the calculation of bending moment. Okay, so that is will now understand why it is simple when it is taken from right to left in case of cantilever beam. Cantilever beam is an exceptional case. You can go from left to right also, but it will save your time if you are moving from right to left, and it will be simpler in calculation of bending moment when I take my section from right to left. Okay, so support reactions we have here 80 kilonewton and 240 kilonewton as my moment. Okay, so this is 80 kilonewton. This was coming out to 80 kilonewton, and MA was 240 kilonewton meter. So this is K in meter. Okay, now let us go with the calculation of bending moment. Okay, so here in case of bending moment, there is no question of concentrated load taking to the right of concentrated load or to the left of concentrated load. I can just go ahead and take the 1 meter interval and calculate the bending moment values. So what I have is first bending moment BM in short at D. Okay, so I'll have my section placed at this point D. Okay, directly at D, and if I look for what the forces to the right side of D. Okay, if I take the forces to the right of D, what are they? Are there any forces over here to the right side of D? So here I don't have any forces here to the right of D. Okay, so what it indicates, our bending moment value is 0. Okay, to the right of D when the section is directly at point D. This is our point D here. Okay, so the bending moment here will be 0 because of no forces are present to the right side of D. Now bending moment at a distance of 1 meters from D. Okay, now what we will do is this section which was at D. Okay, now we'll bring it to a distance of 1 meter because I have my interval of 1 meter. I have to calculate the bending moment or shear force at every 1 meter interval. So now I'll place it at a distance of 1 meter over here. So this distance is 1 meter from point D. Okay, I'm moving from D to A. So at a distance of 1 meter from D. So here what will come over here to the right side of my section. This is my section over here. What do we have is xx. To the right side of this section, there is a force of 50 kilonewton load, a concentrated force of 50 kilonewton. Okay, so this will produce a moment about this section. How much? 50 into 1 meter. The magnitude will be 50 into 1 meter. Okay, what about the sign? Now we'll refer to that sign convention again. So this was the sagging moment. Okay, or if the moments are in this direction, if they are acting in this direction, it will be considered positive. If at all, if the moments at our section, if they are acting in this particular direction, what is shown over here, then it will be considered negative. Okay, now I am looking to the right side of the section. To the right side of the section, if the moment is anti-clockwise, we will have to consider it positive. On the other hand, if the movement towards the right side of section, towards the right side of my section, if the movement, resulting movement is in anti-clockwise, then it should be taken negative. Okay, what is the direction of our this movement due to 50 kilonewton force? 50 into 1 magnitude, and it is acting in what direction? It is acting in anti-clockwise direction. So this is trying to rotate the beam in anti-clockwise direction over here. Okay, so for this I'll assign a negative sign. Why? Here right side anti-clockwise movement negative. Okay, so for that purpose it will be taken as negative over here. Okay, so that is the movement at 1 meter distance minus 50 kilonewton meter. Next, we move by another 1 meter bending moment at a distance of 2 meters from D. Okay, so when I bring it this section, okay, my section by at C, okay, that is by another 1 meter, 2 meters from D. So there, what will be the moment? So here we'll calculate that moment when my section is at C. So distance is 2 meters. So what are the forces to the right side of my section? So here what I have is only this 50 kilonewton force. It doesn't matter whether it are to the left or right of C. You can say I'm exactly at C only. Okay. So here when I bring it over here, what is going to happen to our bending moment value? So now what forces are there to the right of the section is again this 50 kilonewton itself. So here 50. Now distance has increased by 2 meters, 50 into 2 meter. Okay, so that will be the magnitude of moment. Now again, this is having a anti-clockwise moment. Okay, if you just look at the movement direction, this 50 kilonewton load will produce an anti-clockwise moment about C. So for that purpose, it will be taken negative, or this will come out to be minus 100 kilonewton meter. Okay, bending moment at C. Okay, or at distance 2 meters from D. Now this is at 2 meter interval. Next further, if we move ahead, what will be there? If I move by another 1 meter, I'll reach this point B. Okay, the section will be exactly at point B over here. Okay, now what will happen to the bending moment value? So in this case, the bending moment at a distance of 3 meters from D. Okay, I'm taking D as my reference starting point. So that's why I'm telling every time 3 meter from D or 2 meter from D. So here what is happening? Now what are the forces to the right of the section? We have this 10 kilonewton load, okay, and also we have this 50 kilonewton load. Now you have to take the moment of both these forces about this point B, okay, and add them together. So 50 kilonewton load, it is having an anti-clockwise movement. Also, this 10 kilonewton load is also having an anti-clockwise movement. Both are trying to rotate this beam in anti-clockwise direction over here. Okay, so remember that for both the sign will be negative. Okay, so what will be the magnitude of this movement? So due to 50 kilonewton load, if I take that first, 50 into what is the distance? 2 plus 1, 3 meter. Section is at a distance of 3 meter from D, and 50 kilonewton is acting at D itself. So 50 into this 3 meter interval. Okay, so that is one, and it is anti-clockwise movement to the right of section minus, and this 10 kilonewton load is having a movement of 10 into 1 meter. So 10 into 1 meter. Okay, and since it is also in anti-clockwise direction and to the right side of the section, so my sign convention says that it is negative. So minus. So altogether, what is the bending moment at point B? It is 150 and this time minus 160 kilonewton meter. Okay, that is the bending moment at a distance of 3 meter from point D. Right, now we will further move this section by 1 more meter. Okay, so if I move it by another 1 meter, I'll be at point A, at the support A here, exactly at the support A. Okay, so now what is going to happen to the bending moment value? So if you take all the forces to the right side of section, now this again this 20 is also in picture now. So what you have, bending moment at a distance of 4 meters from B. Okay, so what I have is due to 50 kilometer law. Okay, the movement will be in anti-clockwise direction only. Okay, that is there. We have confirmed that. So minus 50, the distance is 4 meters. Minus 50 into 4. Due to 10, again the movement is in anti-clockwise direction. So minus 10 into what distance? 2 meter distance. Minus 10 into 2 meters. And this 20 kilometer load, what will happen to you due to that? This will also have a anti-clockwise movement about this point A. So minus 20 multiplied by distance is 1 meter. Minus 20 into 1 meters. So altogether, what it will give us? This is 200. Okay, and this is 20, 220, and this is again 20, 240, right? And what you have at point A, there is a moment over here. One more moment which is acting over here at point A, right? So what is the value of this moment? 240 kilonewton meter anti-clockwise. Okay. So what should be the sign that will be assigned to that? Okay. Now I have it on the left of my section. These all movements, what I calculated, they are to the right of the section, all these over here. Okay. But only MA is to the left side of my section. Okay. Oh, okay. Just leave it. I will not consider. We'll have to consider only on one side. So MA will not come in picture here at this point. So this will come out to be minus 240. That's all. I don't have to consider MA, sorry, because I am taking only to the right. I'm not considering to the left. So what I have is this minus 240. It will be equal to this MA value. Okay, the bending moment is minus 240 kilonewton meter. Okay, tell me if you want to clear any of your doubts. Any doubts if you have. It should be equal to this MA what we have this moment when we reach the fixed end of that cantilever beam. Is that okay? Okay, if you have written this, I'll just erase that all this calculation. Okay, now let us go for plotting this bending moment and shear force values. Okay, so let's say this is the beam here. Okay, so first is to plot the shear force. So we started with the point D. Okay, so A, B over here, C, and D. Okay, so what was the value of shear force at D? First, initially it was 0. Okay, from 0 it increased to what? 50 kilonewton. Okay, so plus 50 was the value over here. Okay, and it was constant up to the point C. Okay, so at point C, what happened? 60 plus 60, it increased to 60. Okay, and at point C itself, and from here to point B, okay, up to the next interval, it was constant 60 itself. And at B, okay, when I crossed that 20 kilometer road, it became 80. Okay, and further from there to up to the support A, it was constant. Okay, then once we cross that support, it became to 0 again. So this is the variation of shear force, or you can call it as, we call it as SFD, shear force diagram. This was positive. All the values of shear force were positive. So here it was 50 kilonewton. This is 60 kilonewton. This is 80 kilonewton and 80 kilonewton further later reduced to 0. Okay, so this is the variation of shear force. This is what we call shear force diagram. Okay, we have plotted the variation. So at point C itself there is a change. At point B itself there is a sudden change in the shear force. That's what you can observe over there. Next, the bending moment diagram. Okay, we need to plot the bending moment diagram. For that, again I'll take the center line of this beam, a line representing the beam over there, and then what we have to do here is, what is the bending moment value here? At D it was 0. Okay, so this was point D, again D. Okay. This is point D, C, B, and A. Okay, and what I have here, ordinates. I'll plot these ordinates first. At D it was 0. At C, when I came to C, it became minus 100. Since it is minus, I'll plot it on the negative side, on the downward side of this beam, indicating that it is negative. The ordinates will be taken downwards. Okay, if it is positive, they will be taken upwards. So here it is 15 to 200. Then at point B, what happened? It will be 150 plus 10 minus 160. So here it is minus 160. Okay, and at A it is minus 240. Okay, how is the variation? The variation is linear. It is varying linearly. Okay, so this is the variation of our bending moment diagram. So 0 at this point, 150 over here, sorry, 100 over here, 100 kilonewton meter, and here 160 kilonewton meter, and finally this was 240 kilonewton meter. Okay, so this is the variation, and what we have is, this is negative sagging moment. Okay, as to tell sagging moment, the entire beam is sagging. Okay, this is the bending moment diagram, BMD. Okay, you can try for the same beam moving from left to right. There will be slight time consuming and difficulty in calculation. Okay, in case of cantilever beam, I advise you to go from free end to the fixed end, free end to the fixed end, not right to left, free end to fixed end. Okay, so if you have taken that, fine. Make sure that you write down all the notes. Okay, any difficulty in that part, you can ask me, or else we'll finish over here. You can post your attendance.
Ah,